Hey, my name is Omar Slayman, and I've been working on various projects since middle school, including computerized model rockets and flight computers, turbo pumps, FTC robots, fans and engines, and even an imitation of MIT's ionic wind thruster. Last year, my FTC team and I designed a complex robot that stretched my software skills. Here, my multi-level complex state machine stops the intake using color sensors, tunes arm height with distance sensors, uses PID to move the arms, stops with button sensors, and decides what to move to manage power load. For the drivers, I added inverse kinematics for intuitive control of the arms. At home, I've spent 2 years developing and researching this turbofan. I started with an EDF, but after multiple structural failures, I drew on real engines by adding these rings. After, I added a butane afterburner for fun, which led to some awesome footage. I then moved to the next level with a turbofan compressor. After lots of research, I catted everything in Onshape, but after multiple lackluster designs, I started a major redesign. After more research, I spoke with Dr. Harmon, who recommended adding sensors and reading these books. Based on what I learned, I switched motors, added sensors, optimized the airfoils, tightened tolerances, and increased the number of stages to 5. After weeks of test prints, post-processing, problems, reprints, and assembly, I finally had this awesome piece of engineering. Then, I got some test runs and my coveted data.
Something broke.
Something broke indeed. 34 compressor blades, in fact, so let's analyze. As the motor accelerates, some blades shear off, lodge themselves, and fry the overworked motor. But before this mess, low power tests gave some data. While the pressure doesn't change, the sharp temperature increase is a good sign that something is happening. I suspect a couple reasons for this. First, I tried to minimize air leakage with O-rings and a lot of screws, but this design made it hard to fully seal, so I'm going to split this and close these holes. Secondly, the assembly never reached full speed, so I'll need to revisit the motor, materials, and blade designs. But now, with data, I can run these fluid simulations and figure out what airfoils work best. Overall, I love these projects and learn so much from them, but at MIT, I hope to take my ideas, concepts, and skills to the next level through groundbreaking research that transforms how we experience transit and connect with other people.